For those of you who don't know, I'm Leslie Eloise, and I'm Vice Principal and Head of the College of Science and Engineering. And it's a delight for me, as is always, to come and introduce any and all eminent speakers that we have to the university, and Ben is no exception to that. Now, when you are asked to do an introduction, of course, you have to go away and look up for some information, because you can't just say, right, Ben, get on with it. So I looked up Wikipedia, because what better fount of all knowledge is there than Wikipedia? And according to Wikipedia, and it's borne out here, Professor Ben Shneiderman enjoys the wonderful, terrific title of Distinguished University Professor. However, careful digging, you got this wonderful title in 2013, and this was bestowed on you by the university. So I'm just going to call myself a distinguished professor from now on in, but Ben really is a distinguished professor. And he's a distinguished professor in the Department of Computer Science at the University of Maryland. And we're very pleased that you've managed to squeeze Edinburgh into your very, very busy schedule. So Ben was previously the founding director of the Hunan Computer Interaction Laboratory and has received numerous awards over the years. But in the interest of actually hearing his lecture rather than reciting all of them, let me just say that these include elected Fellow of the Association for Computing, the Fellow of the American Association for the Advancement of Science, and a Fellow of the National Academy of Inventors, and I particularly like the last one. And in 2001, Ben received the ACM SIG-CHI Lifetime Achievement Award. And Ben, I suggest that they're probably looking to give you a second one now. So Ben's written many books over the years, many of which you all will have read and consulted, and today he's talking about his latest publication. So I invite him to give his lecture entitled The New ABCs of Research, Achieving Breakthrough Collaborations, and that is also the title of his new book, so we now all know what to go and purchase from Amazon. So, Ben.
Thank you.
Thank you.
I'm very pleased to be here, and it wasn't squeezed in. It was very purposeful. I'm very pleased to be here. I've been to Edinburgh, but not to the university, and so this is a special treat for me. I'm on a bit of a book tour around the country, and this is one that I really wanted to make here. Yes, it is a momentous day, and I hope I can make you remember for something else, as well as maybe, I don't know, the American entry or the British exit. I'm not sure. Today, as some of you know me, and I was pleased to have discussion with many of you for my work on user interface design, on ideas of direct manipulation, about touchscreen design, and those little tiny keyboards on your phones came from our work, or the idea simply that certain words on the screen are highlighted and you click on the words. The link idea was our early efforts, and I'm pleased that those things became part and widely disseminated. Some of you may know also for the visualization work on tree maps and Spotfire, and so I'll say a little bit about those things, but I'm here especially proud to represent the University of Maryland's Human-Computer Interaction Lab, now on its 6th director, and we have a proud history of interdisciplinary work, and I was pleased here to learn about the efforts going on here in the School of Informatics, really large and diverse set of efforts that reflect some of the things that go on here. And computer science is separate at Maryland from the College of Information Studies, but they jointly oversee the Human-Computer Interaction Lab, and this partnerships with many other groups around campus, including the wonderfully titled Maryland Institute for Technology and the Humanities, MITH. If you go to our website, there are 750 technical reports, 200 videos and projects, and so on. So some of you may know me also, and thank you for mentioning the 6th edition of the book Designing the User Interface appeared just a month ago. And so that's been a continuing story of tracking the remarkable evolution of the user interface design issues. By now I've acquired 5 co-authors to help tell this story of how 7 billion people have something like this in their pocket, and they can actually use it, whether they're illiterate or disabled. the people in the HCI community take some credit. Of course, the chip designers and so on had a big role, but I think the user interface people have had an important role, and now the emergence of social media, as we'll see, are important issues. Wrong way. But today is about this new book, which is a kind of meta book. It's a book about research. It's not research, but it's a book about research. And it summarizes 3, 4, 5 years of my thinking deeply and a career of facing research challenges and seeing in my own work what succeeds, has high impact, and what doesn't, and how things travel, and what forms of partnerships and what kind of projects turn out to be important. Okay? So that's the key idea. It was written in part as a guide to students and young faculty about how to conduct their work in the existing research framework in a way that they will have high impact. Of course, we have to find what we mean by high impact, but I think you'll get to see those ideas as well. But maybe more importantly, it's a manifesto for change for university administrators, business leaders, government, funding directors, about how to restructure the research ecology or environment in a way to make it more significant. My claim is that the immense problems of the 21st century are significantly different from those of the 19th or 20th, and it seems reasonable that new strategies of doing research may be needed. Okay? And that's the transformational question. The old methods may not have been so successful even in the old days, and there may be still better ways of doing things. So I was trained in an era that was very much influenced by the writings of Vannevar Bush, Franklin Delano Roosevelt's science advisor, famous analog computer engineer in MIT in the 30s, and the creator of the Manhattan Project. Okay? So at the end of the war, he wrote a book called Science, the Endless Frontier, in which he charted the future for how government research would fund the enterprise. And in it, he describes what's been called the linear model, that you begin with basic or pure research, and then you seek applications. Then, through the process of transfer and translation, you develop products, and then you go to market. This linear model is compelling, it's clear, it's simple. What could be bad? Well, the problem is it rarely works. And over the years, many people have commented about why this was flawed. And so there was a groundwork that spoke to me, and I hope what I've done in this book is to try to take that a step further and suggest not just what's wrong, but how you might change the game. So that's where we're going. The 3 premises of the book are that there are these immense problems: healthcare delivery, environmental sustainability, energy, community safety, cybersecurity. There's many, many genuine problems, and these are characterized by being socio-technical in nature, that they involve more than just a reductionist model in a controlled laboratory study that will solve the problem, that they require a different form of thinking, a different form of study, a different form of research. Now, we still need the reductionist controlled experimentation, but we're going to look to see how other supplementary forms of research might extend, amplify, and improve the work. Second premise is that we can deal with these immense problems because there are new technologies. The emergence of the web has dramatically changed things. Social media, communication strategies, and visual design, visual communications has dramatically changed what people can do. And so it may be possible that research teams could take on far more ambitious projects, and that's where they go. Okay? So just look at the way the technology has changed the capabilities. 40 years ago, the average researcher read 175 technical papers a year. And those typically came from 6 or 8 journals that they subscribed to or their neighbors did, and they read those journals in fairly solid depth. Okay? By now, the average researcher reads 400 papers a year, and the majority of those recommendations come from social media sources. They come from email, from listservs, from colleagues recommending something. They come from Twitter and Facebook and YouTube and beyond. All right, so there's a radically different social environment, and these tools enable people to find out what's happening. When my students and I come on to a new topic, we've been working very strongly on electronic health records. Some of you heard me speak about that yesterday at the Farr Institute. And when we get a new idea, when we have a new question, within hours we can read the top 10 papers or get them and take a look what's going on. We can find out who the key research groups are and who the leaders of the field are. We can begin to make bridges to them. We can ask questions to them. We can form collaborations if we need to. And those capacities are potentially a game changer and amplifier for the capacity to do research. The raised ambitions are that teams are taking on much more than they used to. 30 years ago, a typical medical study might have been 800 patients at a single hospital with a certain new treatment medication. Now, a paper might be 10 hospitals with 800 patients each around the world in very different circumstances. And so the idea that the papers include a form of replication and validation is increasingly accepted. And so we see much more ambitious projects going on, and of course with it, much higher expectations from those who fund research. Now, you may be troubled by this as a researcher who wanted to work on their basic and pure research in their ivory tower, as it's called, and to be, as Vannevar Bush said, unfettered, and to be able to do your work. And those days are probably mostly gone. We may mourn them. And we have the pressures of government funding and the expectations that we add to the nation's benefit, to the knowledge, to the economy, and so on. So there are new pressures, and they manifest in different ways around the world. So we could discuss these about, what are the realities that have changed, but I think these are substantial ones. And the problems being socio-technical in nature, I think, are a big shift, and that if we're going to deal with smoking cessation, obesity reduction, we're going to deal with cybersecurity, we have to take things on at a massive scale. But the tools are there for us to do it, is what I claim. So the guiding principles we need, I cite two. Okay? The first one's the title of the book, and maybe the most controversial one, that says, if you do applied and basic combined, ABC, you're likely to have a better outcome than if you just worked on one of them. Okay? This is raising the expectations for teams. Okay? And the basic notion is to work on a real problem, bringing a theoretical perspective, and partnering possibly with those who have the real problem, and not just getting the problem, but working with them, developing a potential solution, implementing it at scale in the real world, coming back to refine the theory, publish the theory, and disseminate the solution. That's the twin win. That by working on a real problem, you're going to get better theory. And so I'm shifting from what I see in many fields as toy problems, synthetic data sets, and self-validation within the group. The team, if they form it, looks at it and they say, yes, we did a case study, we tried it out on a data set. But I think a more valid test is if you work with real users on real problems, on real data, that someone outside your group becomes the one who gets to use your tools, your ideas, your theories. After all, Kurt Lewin said, there's nothing so practical as a good theory, so we ought to take that. And he also said, if you want to understand something, try to change it. And this notion of intervention at scale becomes possible. Never in history have so much of what people do been online and available, and it's just the beginning. And never before have we had the powerful tools to analyze at scale what is happening. And so the potential for far more ambitious projects, I think, is quite real. Okay? Now, Vannevar Bush argued in the linear model that basic research inevitably leads to applied results. And that's not true. And that's where things have gone wrong. And in fact, there's many times where the history tellers, the storytellers, revise the history to reframe what happened. So applied research has always been a strong driver of success. Bell Laboratories, famous for this. Arno Penzias, Robert Wilson were asked to find ways to do microwave communications for Bell Laboratories, and they got this persistent noise in the background. And what do you know? They get the cosmic background radiation, for which they win a Nobel Prize. And some of those histories tell it about, here was a great case of basic research, and actually it was a great case of applied research. Maybe the poster child for this notion is Louis Pasteur, in Donald Stokes' book. Pasteur's Quadrant tells this story quite well. Pasteur worked on the problems of fermentation of wine. He worked on the spoilage of milk. And yes, he gets pasteurization and improved, but he gets the germ theory of disease. That's a pretty big payoff. And one after another, if you look at the way the histories are told, and you read it through this approach, I think there's a pretty good argument, not always. I mean, there's still room for the lone theorist and the solitary tinkerer. I mean, after all, Niels Bohr was that the lone theorist, and Thomas Edison was maybe not quite solitary, but he was a tinkerer and not a scientist or theoretician. So there's always been exemplars of these different versions, but I would say increasingly, Pasteur's quadrant is the place you have the greatest potential for the highest impact, both in theory and in practice. That's the twin win. That's where we're going. Okay? Now, I've had pushback on this theme, and but I must say I'm quite pleased by the widespread acceptance I've got. There's a very nice review in Nature that supports the book strongly, and so that made me smile for a while. And several physicists have said, yes, I've noticed my big successes are when I work on a real problem that's somebody else's problem. Okay. And we could analyze different stories if you want. So the second guiding principle, maybe not as charmingly titled as the SED Principle, Science, Engineering, and Design. I was also trained in the world of science. Thomas Kuhn, Structure of Scientific Revolutions. Okay, science was research. Okay, then in the US, the National Academy of Sciences was founded in 1863 by Abraham Lincoln. The National Academy of Engineering was founded in 1964, okay? 100 years later, after World War II, when engineering became a research discipline, okay? The National Academy of Design was founded in, it's a trick question, there is none. 2064 is what I propose in the book. It's still a more emergent discipline, and there are academies of design in England and other places, but it's still sort of an emergent theme. But what I came to see is that although I was trained in science as a physicist, particle physics, engineering and computer science where it was, I'm a member of the National Academy of Engineering, okay? And my book is called, if you notice, Designing the User Interface. So in my trajectory, I've seen these are different ways of getting at knowledge. That the method of science that I was taught, which was the way of knowledge of reductionist model, laboratory studies, controlled environments, still valuable, but it turns out that's not always effective. Okay? And even in the place of medical randomized clinical trials, there's lots of people questioning their efficacy. Okay? So what does engineering bring to it? Okay? Engineering is another way of getting basic knowledge. Engineering depends on setting goals, requirements, making measurements, starting out with pilot versions, scaling up, repeated testing, modular design. There's a very useful set of principles that engineering brings to the table. Design thinking is the newer kid on the block, and there are many, many definitions. In the book, I have a whole chapter of what is science, what is engineering, and what is design. And I think design still is settling in, but the central tenet of designers is to question the goals that are given and to reframe the requirements And as the British Design Council calls it, there's the divergent phase of thinking of many alternatives, converging, and then diverging again to find solutions, and then converging on a solution. This double diamond has become widely replicated and built on as a notion. So it's a much more open-ended process, and then it takes on this unique quality of empathy. There's a strong component in the design language about thinking about the users, understanding how people work and use the designs. Now, some would say, and many of the scientists would say that design, oh yes, design's fine, it's good for designing postcards and posters or, watches maybe. But I make a stronger claim, and they do also, that design thinking is yet another way of making contributions to knowledge, of trying to understand the world and the relationships of components, and therefore how we can build those components more effectively. So it accesses a kind of knowledge that science can't get to. And designers resist the pressures to be scientized, they say. There's a strong assumption among scientists that science is the right way, and once you get past your early stages, you will come to the methods of science. But the designers say no, and they have a strong case to be made. So, this was the writings that I was reading. These were the personalities I was exposed to, and there were good examples of design. I mean, some design, of course, has engineering components to it, chip design, software design maybe, building design, structural design. But there are other parts of design that go beyond what's usually considered as part of science and engineering. And so those areas of social design, of community design, of interface design, of web design, are somewhat different and not usually covered by the usual science only or engineering only. So I was, wrestling with this issue over several years as to whether did I really believe that SED, that design would take an equal position. And along the way, you may know about the Google Ngram browser, 20 million books in English online. You can search for any keyword, and I did this search of engineering, science, and design. So engineering, this is from 1900 to 2000. Engineering, frequency of the word engineering wiggles along, science wiggles along, and then in 1975, design crosses over and becomes a dominant topic. That was pretty interesting. Didn't know if I could build a whole book on that, but it was pretty interesting. It wasn't just Steve Jobs and Johnny Ive who did that. They were part of a movement that was already in ascendancy. And so that sort of led me further, and I spent more time reading and studying design and trying to assess its value. And about 2 years ago, the New York Times put online its Chronicle database of all the articles in the New York Times, and I did the same thing from 1900 to here 2010. The word scientist wiggles along, the word engineer wiggles along, and here the word designer now in 1975 crosses over. Well, 2 data points sort of strikes me as a lot more. 2 independent data points, or mostly independent data points, strike me as a stronger. So these 2 figures are in the book for you to contemplate and argue with, and let you think about whether that makes sense. I did write an essay in the Times Higher Education on can design thinking challenge the scientific method as a provocation? And the answer was, of course, no, because they're separate things, and you should do both, and you should teach them to your students. So that's kind of one of the current issues of how do we change and open up the curriculum in science to also include engineering thinking and design thinking. I was very pleased to hear a description of your close collaborations here in the School of Informatics with the School of Art and the Design, and that design thinking is part of the curriculum. So I think that's on the right track, and the point is to be open enough to take that in as a goal. So the book proceeds, and there are 5 chapters, and maybe I just should walk them through a little bit more slowly here. The first is about choosing problems, how we teach our students what problems to choose. Peter Medawar, Nobel Prize winner, biologist, British, wrote a book, Advice to a Young Scientist, and he says, don't choose piffling problems. And that's often recited, but we don't get to know what a piffling problem is. And there's very little guidance, and I realized I had very little guidance about choosing problems. Many students come to work with a mentor, and they take what the mentor tells them to do. But I would say there's an increasing number of opportunities of finding out what are the important challenges in the world, whether you follow the British Longitude Prize, or the National Academy of Engineering has 14 grand challenges that they think are central. They've done a collective process. You can look at innocentive.com, an online website where companies post challenges, and solvers, 500,000, including me, have signed up to read these and work on problems that companies care about, and this has driven a lot of progress. There's many other science, engineering, and design roadmaps and other ways that young researchers and students might learn about potentially important problems. Now, it's important to recognize in choosing a problem, you may say, well, cancer is a problem, I'm going to solve cancer. No, I mean, if you can, that's an unrealistic ambition, but if you say, well, I'm looking for an improved test to detect breast cancer in blood earlier than others, all right? There's a kind of narrower and more well-focused goal that could drive some breakthrough understandings. Okay? Now, the second part of that, of choosing problems, is to work with civic, local, or national government agencies, business partners, or global priorities. Again, I'm pleased to see that's an important agenda here, that working with companies and the innovation culture, entrepreneurial, is a part of what goes on here. It shouldn't be the only thing, but it's a way of exposing students to realistic problems and finding partners. This partnership theme will emerge, and I'll focus on that. Okay? Second, the methods I came to understand of, again, controlled experimentation were the traditional ones, but observation and increasingly intervention at scale becomes what we can do. And so several of the case studies in the book talk about how people have created interventions that produce large benefit. My dear colleague Rita Colwell, who was president of the National Science Foundation early on as a microbiologist, studies cholera in Bangladesh and works with her team of researchers. You may know cholera spreads by the cholera bacteria, but it's not that it's floating in the water, it's that it's attached to the surface of these little bugs called copepods, about 1 millimeter, 2 millimeters big, okay? And if you swallow those with tens of thousands of bacteria, then you're likely to get cholera. And so she developed a very sensible, simple solution. If the women in the village would just wrap their cotton saris 6 or 8 times and pour the water through it, the copepods would be trapped, and the water would be noticeably clearer in the beaker below, okay? And that's the science that she knew that gave her an insight. And then it was a matter of engineering a solution and making a design of a public health policy. She worked in 19 communities in Bangladesh and trained people to do this, not just once, but every time. And she worked with the hospitals to track the data about how many cholera patients there were and how many deaths. And she did find a statistically significant difference. Okay? She came back with that, refined her teaching methods, the design of the strategies, the education, the data collection, and she comes through and has this wonderful breakthrough of 48% reduction in cholera, and the study was with 133,000 people. Okay? That's kind of a remarkable intervention at scale that has a dramatic effect. I mean, few of us will ever do a project that has that kind of direct, immediate benefit, but that's a pretty remarkable story to tell. Okay, so that's the notion of intervention at scale, not in the laboratory. We'll take a look at teamwork. That seems to be the central issue and the biggest change that's happening for many of us. Then the idea of ways of testing ideas and prototypes, realistic interventions, ethnographic combined with big data, I repeat that we are able to log at scale in a way we never could do before, and yet we find the great power of the thick descriptions, the in-depth ethnographic interviews for many problems as well. The last is also controversial. I'll have a few notes about it, but my colleagues often say, my research speaks for itself. I published it in a refereed journal, and it's out there. And that may have been true a long time ago, but in the current world where 2 million papers are published a year, it's, I think, no longer true. And so being able to tell about your work and describe it in a variety of ways, to report on it in different media, in different formats, becomes increasingly important. Remember, the 58 million articles in the Web of Science, about half of them never get cited. You don't want to be on that, okay? And the small, another 18 million get cited 1 to 10 times. And those that get cited more frequently are more rare. So you want to find out what works to get news out there. Now, the best thing you can do is to write good papers, to tell the story in an orderly, logical, clear way. And I became a great believer in clear writing to actually shape the thinking. So that's another story. And then assessing impact. It used to be science citation counts, but I think we've moved on to a variety of ways of assessing impact, and not just the quantification by the number of citations. There are many other ways that people come to value the impact of research, not just its science contribution, but also effect on policy, effect on training, inclusion in textbooks, economic spin-offs, patents. In the US, more than 45 universities have already changed their hiring, promotion, and tenure policies to include patents giving equal weight with publications. Okay? So there's a shift in these attitudes in a variety of institutions that I think is important for our students to be aware of. Okay, the goal here is then the twin win, that you solve a problem and you improve a theory. And my argument is that if you take these approaches, you'll get better solutions and better theories at once. Okay? So let me just say we could end here or maybe just go for questions, but I think I want to take a little bit more and focus on the teamwork issue, because that's the thickest chapter, the most citations, and I would say the most rapidly emerging area. Well, that's our team. That's the Human Computer Interaction Lab at the recent CHI conference in San Jose, Computer-Human Interaction. So we're about 35 or 50. It's not one team, but it's kind of a team of teams. And we work together and support each other in ways that are appreciated by our colleagues. So we have an annual symposium, just was May 26th in College Park. 29 presentations in that day-long symposium, students and faculty. Every one of them was rehearsed. They're 14-minute presentations, and everyone gets a 14-minute practice with 15 minutes of discussion of their work, people critiquing them. It provides a supportive environment that's quite rich, and the goal of everyone is to make everyone's work better. Okay? When we have conference deadlines, 2 weeks before the deadline that many people are contributing to, the papers go on the wiki, people sign up to read them, and we have a meeting, a half-hour meeting about each paper that's been, the draft of each paper that's been submitted. And we discuss them. Those have been my most interesting intellectual days in my campus life, because there are people talking about work. You thought you understood it, you had a view of it, and suddenly you find there's a fresh perspective that reveals things you didn't know about. So these are kind of some of the social ways. We also have regularly Thursday lunch. Come join us sometime, and 35 to 50 people, 70 people sometimes show up for this. Sometimes we have outside speakers, okay? And sometimes we have speakers from around campus to let us know what's happening. And about a third of them are the students, usually, talking about the work they are going to do, describing their proposal, their plan of work, and then everybody chimes in. And so everybody knows what's happening around in the community, and then the goal, of course, is to improve the quality of everyone's work. Those are some of the kind of teaming structures that we use, but the notion that we're publishing in group teams has become quite dominant. If you don't know this result, for science engineering, that red line, it goes from about 50% being written by one person to only 10% being written by one person. That teamwork has gone 90% of science and engineering publications. When I was a graduate student, I published my work single-authored. By now, we publish as groups, and the work is richer. It's more ambitious. There's a student who's their PhD. It's unique. It's their individual PhD. But the other students working on our electronic health records, we all try to help them. And sometimes we make substantial contributions and they become co-authors. We spend a lot of time discussing who's the first author, who's the second, third, and fourth author. Am I on it or not? Sometimes I'm not, okay, because of the contributions I may have made. Okay? So teamwork in writing is more common. Just for example, in astronomy, in 1965, the most number of authors on an astronomy paper was 8. Okay? Now, on some papers, there are 1,000 authors. Okay? Those are extreme cases, but these group efforts, and the LIGO or the Large Hadron paper or the gene sequencing paper are 1,000 authors. Interestingly, also, this is social science, which has a distinct upswing in the mid-90s. Any guesses why? End of communism. Whoa, I wouldn't have said that. That's an interesting association. But internet, right. My guess is that the rise of the web as being more widely used turns out to be the case here. Okay, so it's apparent that teamwork is happening, and I would say the ambitious level of effort, when I graduated, I had 4 pretty good journal papers published. That was a pretty good record. Now I see students arriving, applying to work with us with 20 papers. Okay, some are conference papers or workshop papers, but there's quite a strong mix. They've exposed themselves. They've put them out there. They've tried ideas. They got feedback. They improved their work. And I think the quality of work is much greater. Now, the skeptics may say, oh yeah, there's more teamwork, but the quality of work has gone down. It's the least publishable unit idea. The minimum publishable paper is what people go after. I don't think that's right. The conferences I go to have 15 or 20% acceptance rates, very competitive, and I would say the quality of work is generally very good. Not everything's perfect, but it's pretty strong. What gets published is pretty strong from especially the good refereed conferences. So that's one way to look at it. Another question, becomes what about the impact of having groups? They may be more people working, but the quality is lower. And not true again. The evidence, very nice set of studies, shows that even 50 years ago, papers that were authored by 2, 3, 4, up to 5 people had higher numbers of citations than single-authored papers. 1.7 was the factor. Okay, so 70% increase of citations if you work with others. And it's not just because you have more friends and you cite yourself and all that, that's discounted, but likely you can imagine that teamwork actually produces fresh ideas. It produces new ways of thinking about problems, okay? And that's where we're going. We're going to look at why teamwork might work. These days, just to finish, that number from 1 to up to 5 authors has a 2.3 payoff, 130% higher impact because of teamwork. And I suspect because internet communications technologies, social media, Skype, shared documents, shared data sets enable people to work together far more effectively than they could in the past. So the question then becomes how to do this. The book has 12 little stories or 12 features, I hope documented with evidence, that if you want to make a successful team, get people who have been on successful teams. That may seem recursive, redundant, but it makes some sense. If you have people who don't like working in teams, who want to be solitary, and you force them to work in a team, that's not going to be very good. So people who have figured out how to work in teams are more likely to be successful researchers. Okay? So you want to find those people. Then the balanced team idea. Now this is really tough. There's lots of kind of balances. You may want a data mining person and a person who's a theoretician. You may want combinations of people. You may want different ages. Good evidence that mixtures of old and young researchers on a project make the project come out better. Gender balance is another issue, very controversial. That's, and then personality differences. Good teams are not quiet places where everybody says, yeah. I have had a collaboration with Catherine Plaisant for 28 years, and we regularly disagree, sometimes strongly, respectfully. But whenever she says something and she disagrees with me, I pay attention and listen. Because there are different ways of looking at the world that I may not have realized. Sometimes it's very simple things like one person on the team says, look, the conference deadline is June 15th. Whatever we get done, let's publish and submit by June 15th. And the other person says, let's get this one right. Let's take our time. Let's do it really right, and we'll publish it when we're ready. Now, those are both valid arguments, and working that out turns out to be a very powerful principle. And so those are small and administrative issues, but substantive issues about how to do the research, what topics to take, how to evaluate things become really important. And those personality differences, evidence shows the diversity does help. Okay? At the point where it breaks down or groups go bad, and groups do go bad, then it becomes a problem. So learning how to make a group succeed is important for managers, team leaders, as well as for team participants. There's a set of readiness skills that actually people need to have. Okay? They need to be willing, eager to work in teams, I've mentioned. Fluent with the technology of Skype, shared data sets, shared documents, how to do it. Okay? So you don't waste a lot of time, make mistakes, or just lose energy. And then some projects require remote working across time zones, across cultures, across languages, and those require yet further skills. Every time you add a teamwork component, you raise the complexity, and you may think that just, has an endless problem. But every time you add a partner, you gain strength if you do it right. Okay? And so, okay, one more is that sometimes teams need experienced leadership and administrative people to, purchase equipment, arrange travel, or hire or fire people. So those become yet another component. Once you've formed the team and you're now off and running, managing a team is yet another opportunity to get it right or get it wrong. Okay? So the key thing is there needs to be within the team clear, defined goals and roles. Goals and roles. If team members think the goals are different, not very fruitful chances of success. If they're not clear about who's the one who's getting the data and who's the one who's cleaning the data and who's the one who's going to write the programs, then you run into trouble. So it's better if you define what are the goals and what are the roles. Then explicit statements of who does what by when. In my classes, my students, I range classes 3 to 5 person teams, and there's 2 rules I teach them. The who does what by when. So Michael says, I will write the first draft by Tuesday, 6 p.m., and Charles says, I will give you a review by Wednesday at noon. Okay? And the fulfillment of those small commitments builds the trust. Sometimes it's just as simple as saying, I'll send you a paper by tonight, and then doing it. And those little things build up the trust that makes for bigger requests and bigger commitments. Okay? The Google studies of their own teams, of 180 teams within Google, showed that the key factor of success in their study was what they called psychological safety. That someone could say, I was supposed to do this by today, and I've had family problems, I've been unwell, or I just couldn't figure it out. And they feel safe to express their failures and move on, and they say, okay, we'll jump in. Thanks for letting us know early enough that we can fix this. And so that kind of who does what by when. And the other is something small soon. As I suggested, even small commitments that get done allow you to build up and have more substantive commitments later. Okay? Good communication is often described, and what does it mean? How do we listen well? How do we speak well? How do we write well? These are, whole long issues. But the evidence is very clear that teams where there's balanced discussions, where the team members speak more or less equally, are much more effective. One person dominating is a bad idea, you could guess, but also 2 or 3 people who don't speak up ever are a bad idea as well. Some teams institute even, artificial policies such as nobody could speak twice until everybody spoke once. Some teams even impose, rather than a voting notion, a consensus notion, and require complete consensus that says, look, we have to make a decision about our research project, and we'll make that decision with everybody agrees. Now, that means people can disagree, but then they say, look, I disagree, but I'm behind this. I support the idea. I'm going to put my shoulder to work in the way you say, by the deadline you say. So these strategies for building teams are increasingly being studied and increasingly well understood. Having a regular and open discussions are important. Our group meets Thursdays at 2 o'clock from 2 to 4. Sometimes we cancel or it's shorter, but there's no haggling every week. When do we meet? When do we meet? And it's always Thursday, 2 to 4, and then we may adjust things. And then the discussions are for everyone to be part of. It's not like there's a leadership group which makes, important decisions. Effective brainstorming, it's not a matter of getting Post-it notes and everybody talking in a room. There are well-established strategies about how to get divergent thinking independently going, how to do parts of projects separately, pool ideas, look for differences. They're very powerful methods worth learning about. And this divergent followed by convergent. And then finally, again, larger projects will need some administrative rules to keep it going, manage the money, and deal with things. So I think that gets you there. There's a bunch of interesting books on this that I was inspired by. Last year, the National Academies came out with this very interesting book, free to download, called Enhancing the Effectiveness of Team Science. Worth reading, well written, well documented, and lays out a set of issues that make clear about how the research is going and what research is needed about team science, team engineering, or team design, as it were. And that book breaks out small teams of 2 to 10 people as one category, as relatively well understood, but the larger groups, 10 to 1,000, are much more difficult to control, and so understanding how to manage them is important. If you want enjoyable read, if you're in the computing field, Walter Isaacson's book, The Innovators, brilliant, wonderfully written history with key figures, and then he also gets the idea that teamwork, the role of women, a variety of very important issues, the role of AI versus human control, etc. And then this book focuses on partners, two-person partners, Lennon and McCartney, and Watson and Crick, and so on, that he advocates two-person teams, but this Stephen Johnson's book advocates larger networks. So those are kind of interesting views of it. I think I'll just stick here. I was thinking, the question in the back before I go on about, the way, for example, funding agencies would support funding. Another important points I noticed as I was working through the book, I was looking for those events and attitudes that were aligned with this kind of thinking. And one of them was in the National Science Foundation. There's a program called Algorithms in the Field, AITF. If you search on AITF and at NSF, you'll get it. So Algorithms in the Field is mostly for theory types and algorithm developers. And it says explicitly, we encourage proposals from theory computer science people working with domain experts. on real problems. And I thought that was really the right idea in terms of finding a balance between this and how, rather than working on your own, working with someone who really has the problem, I think becomes the important idea. All right, I think I will sort of say, maybe come, how are we doing on time here? I wasn't, there we are. Oh, we're really, okay. Yeah, so let me come to a close here. Just one point about this adoption and impact. It's a matter of going social and opening up your attention to the different ways that you could have impact and you could reach out. So going around and talking, presenting, turns out to be a good idea. And so practice your presenting skills and get out there and do the presentations. It's a very good way of spreading ideas, okay? However, here's a little trick that I think will show you the way my thinking has been going with my students. So the scenario is you've just had a paper accepted for publication. You've got 2 weeks to revise it for the final submission, okay? And I tell my students at that point, okay, look at your paper. Go to the references in the back and choose the 5 people who are the most significant contributors to this area. Get their email addresses, and then write each of them a personal note that says, "Dear Professor so-and-so, I am a PhD student at School of Informatics in Edinburgh, and I'm finishing a paper and submitting in 2 weeks from now for publication. It's been accepted, and it heavily cites your work. I have 2 questions for you. First, have I been fair in describing your contribution to this area? Second, have you written anything more recent than I should be citing in this paper?" Okay, that's it. Short note. And I'll make you a bet that you get 80% response within 48 hours. Okay, when I get notes like that, I read that because I want to know what people have done, and I want to see how they're describing my work, and whether they're a professor at Shanghai or Harvard or wherever they may be. I think you'll get those kind of responses. So the students, when I tell them this, they suddenly have this sort of shriek of fear because they realize, oh my gosh, they look at their paper and it says, "Professor so-and-so's work failed to do this and that, and this paper fixes this grievous omission." Okay, and they realize they can't write that. But the fix is easy enough because the rewording is, "Professor so-and-so's pioneering work can be fruitfully extended by the ideas in this paper." Okay? And my point about that is to convey to my students that I expect them to be in touch with leaders of the field. They are a leader of the field. I expect them to do significant work, and I want them to see them as partners and collaborators. And they have to come to recognize that science is a social process. And you need to make the connections for doing your science, your engineering, or your design. You're part of a community. And that central notion that you're part of a community, you're collecting support from people, you're telling about your work, you're making your contributions, is really an important aspect of this. There are many ways to make contributions, and that's what I want people to think about. So I think I'm going to cruise through here and just close by saying the basic message is applied and basic combined, and then the goal of teamwork is to achieve breakthrough collaborations, that creative ideas are what you're after, that you're going to build on your connections, and ask bigger questions is the sort of punchline at the close there. And that's where we are. So I know some of you have to leave, but thank you for your time and attention. I'll be glad to discuss and engage more. Thank you.
One of your graphs shows how we think the internet improved teamwork, and therefore the idea is non-geolocation. And on the other hand, you're talking about it's nice to have regular lunch meetings, which is fine when you're all together. So how important is the physical co-presence in teamwork in this way?
It is important. I mean, the famous set of papers, Distance Matters, by Judy and Gary Olson in 2000 tells the story. And in the last 15 years, they reiterate the fact that even if people are on different floors of a building, Michael was telling me that here the building was designed to make fluid motion across floors, those things matter as well. So being close by and fortuitous encounters are very powerful. However, sometimes the people in your building don't have the skills you need. And if you have that thought process that says, I can work with others, the technology can enable you to make those kind of long-distance collaborations. Don't underestimate how hard they are, but they become possible if people are fluent with these collaboration technologies.
In this kind of strategy, we're very focused on our goals and our direction, and we're working within teams. How do we also make it so that we're aware of any implications to other problems that can provide this breakthrough?
Yeah, well, I think if I clarify the point is you're suggesting that if you're more goal-directed or more applied, you'll have greater difficulty than if you were simply basic research to know the applications. I don't see that. I mean, I see, and the history is of people working on basic ideas are not connected for people with real problems. They're unaware, and their work will often go unutilized, maybe 30 years or 50 years later. But Vannevar Bush's line that inevitably is just not borne out by the evidence, and that people who are engaged in applications and then network to other application domains turn out to be successful. The Innocentive website makes a special case of this, that the goal of writing a problem description is not to be super technical and include all details, but to use generic enough language that people in nearby disciplines will be able to take a hand at solving a problem. And so this porous or open attitude can be helpful. Those who wander across campus to attend a seminar somewhere else or keep their minds open could be important. Bridges, gateways, gatekeepers. I'm on a National Academy of Engineering panel. I'm a steering committee of 12 people that is held a 140-person conference about the relationship of art, design to science, engineering, and medicine. Okay? Now, I'm somewhat of a skeptic about those long-distance bridges, but it really was quite interesting to see how those who believed and had examples about how those bridges could be helpful. So I might say there's many flavors of bridging. In writing the book, I wrote a whole chapter about interdisciplinarity, which is seen as this glorious thing. And then I threw it out. Okay, interdisciplinary, cross-disciplinary, transdisciplinary, all those celebrations. And it turns out the evidence is weak for that. The evidence is much stronger for working with people with problems than it is just going out to another discipline. So the KDD conference, I think you're going to. The KDD conference, knowledge discovery data mining, more than 1,000 papers submitted, 14% accepted, 140 papers accepted, pretty tight, okay? And the analysis showed that the papers that were co-authored by people in university and business were statistically significantly higher rated than those that were all academic or all business. That was a pretty strong signal for me, and I've since found further evidence of that. Interdisciplinarity in general is more of a challenge. You have to be careful about it. Skills, yes, but disciplines, be careful. So I posed as a listserv on interdisciplinarity, and I posed this question. Is a computer scientist theoretician working with a computer scientist system builder interdisciplinary? 50-50, yes, okay. Is a computer scientist working with a molecular biologist interdisciplinary? Yes, yes. Is a computer scientist working with a dance choreographer interdisciplinary? Oh yes, that's wonderful. Okay, so there's kind of an enthusiasm for the long distance interdisciplinarity. However, I think you can probably guess that if a computer scientist would be fine if they worked with a choreographer, and maybe something good would come out for computer science or for dance. But if I'm allocating the tax dollars, I have to question what fraction of the money I would put there. Maybe it's 5%, maybe it's 10% for a especially good set of proposals. But I think I'm more likely to get fruitful payoffs from the biologist working with the computer scientist or the two computer scientists, depending on what they do, of course. But I think we have to understand there are different forms of partnership. I'll just restate the summary. I believe that working of researchers, academics, theoreticians who work with people with real problems are more likely to have payoff than just going interdisciplinary. So the chapter on interdisciplinarity went out, and then it came back in as a section within teamwork. It's one of the forms of doing teamwork.
I like the idea that challenges are set in a broader area. They're identifying areas in which progress made would have a social impact or an industrial impact, and then gathering multiple teams which form a community to contribute into an area, which builds then up opportunities which everybody from individual researchers through students to larger teams and funded programs can then address. And I think a lot of what you're saying would apply in that area, but the idea that you build a community that shares a challenge problem and then addresses it with science, addresses it with engineering, addresses it with design, would seem to me to be a logical way of extending what you're talking about.
That sounds reasonable. I guess I'm most familiar with the small team formation of 2 to 10 people. That's kind of where I go, but I gave the example of our lab, which is sort of 50 people, which I'm no longer director, but I have a sense of forming that and pushing it down the road about those topics.
I see this across an international scale, where you're dealing with people with very different issues, very different problems. Some of them can get funding for certain areas. They find their own problems within challenge space.
Right.
That's the difference.
The
It's
question
not one problem.
is, is what degree of cohesion among these team of teams? That is, are they funded under one body and then they have to deliver, or are they independently funded, they find their own funding and so on?
You see what I'm doing? I'm taking those apart by saying, I think all your 10 would apply. All your 10 points would apply, but they may apply very different to an individual PhD student in a country that's not funded by any national program. But he could still be a member of the community contributing and feel a member of it. You said some of those things. I wasn't criticizing, but I think it would extend what you're talking about. It would make a great additional chapter in edition 2.
Second edition. Thank you very much. This is available from Oxford University Press. I'm happy to say it's published in the UK. And thank you for your comments, support, your nodding support, your challenges, and thank you all.